Okay, so we come to the last lecture of this class, and we conclude it with what is called faulting. You must accept that I had to squeeze in a lot of things, and I'm not happy, but that's what it could be done in this time. Normally I take about 52 classes in a normal semester, but this is almost 12 classes less. But anyway, we do it, whatever we do. Now, faults, there are essentially two types of faults, and we can divide it by a line drawn through the middle. We can divide it by a line drawn through the middle. These diagrams were drawn by my student. This is much better than me on this. So these are called, on the left, these are called irrotational faults. And these are called rotational faults. Essential difference between an irrotational fault and a rotational fault is the following. In a fault is a plane that separates the hanging wall. You have a hanging wall and the foot wall. So the structures were continuous before, and then when it faulted, there is a plane generated. This plane is called the fault plane. And in an irrotational fault, the structures that are there in the foot wall, they have the same orientations in the hanging wall. Same orientation, not the same position. They have the same orientation. Say, for example, there was a horizontal bed, a vertical dike, which is faulted. The fault does not change its orientation after faulting. Right? That's about irrotational faults. And in rotational faults, the orientation of the structure changes. The orientations of the structures changes. That's the two difference between rotational and irrotational faults. Now, there are several ways in which doing it. Irrotational faults are generally brought. What did I do? Okay. Why is there two?
This is better.
Okay. So, sorry. Fine. Irrotational. Now, in irrotational faults, there are essentially three types of faults. One is called the normal fault, and this we have discussed before, where say for example, you have a horizontal bed here, and that is displaced. So the foot wall moves downwards relative to the hanging wall. At least it appears so. Have you understood? So what is important is the foot wall relative to the hanging wall, the foot wall slides downwards. So there is a displacement of the structures with the foot wall going down relative to the hanging wall. My God, my student has completely
Sorry,
my student has completely gone around mad. She missed it. That is why I was getting a little confused. This is the foot wall, and this is the hanging wall. Foot wall footwall and hanging wall. Now, the point here is so there's a mark of it, and you can see this mark of it has been displaced downward in the hanging wall. Say, for example, if there was a dike like this, this would have shifted in this direction. This would have shifted in this direction. Here, if you had a dike, and it would have shown a shifting. What's this? So what is happening is, this is the fault plane. In all of these cases, this is the fault plane. This here I can't show you. This is the fault plane. Now, I told you why it's called a footwall and a hanging wall before. So, I don't go into that. The important point is, there is something called a normal fault, where the hanging wall moves down related to the footwall. And then there is a reverse fault, which is the hanging wall moves up with respect to the footwall. And there is something called a strike slip fault, where a footwall moves parallel to the hanging wall. It's along the strike of the fault line. Now the point is, how do you identify a fault line? Normally what happens when two rocks side by side, and the two rocks are, when they move slide past another, remember this is brittle deformation, there is no bending involved. When moved past other, then there is tremendous friction generated. A tremendous amount of friction generated. So what happens? The rock surfaces along the footwall, they crush each other. So if you look at a fault plane and you put your hand on the fault plane, it looks like glass. It just looks like glass because of the tremendous amount of abrasion it takes and the material slide past each other. And sometimes what happens due to this crushing, there is a lot of powder-like material that is generated. This is called fault gouge. This is called fault gouge. This is called fault gouge. It's like talcum powder. You can put it on a paper and you can put it on your cheek, and it's talcum powder. It's finer than that. And so much of this material is where there is crushing of the two rocks at the contact line. So you see a lot of fault gouge in the plane. And then if you see the plane exposed, the fault plane exposed, you see lines like that. Lines like that. And these are called slicken slides. These are called slicken slides. These are called slicken slides. They are grooves. They are grooves along the fault plane. Say, for example, there is hard something on one of the plates, and when you slide it past the other one, it cuts a neat groove along the fault plane. And they give you the direction of the slip of the materials on the fault plane. These are called slicken sides. Now what happens when a material moves down very strongly against another thing? So there is this striations. If you move your finger parallel to the movement of the fault plane, then it appears like talcum powder. It's like a talcum powder. You will see smoothly your finger moves. But if you move your finger opposite to the direction, then it will simply bleed because your fingers will get cut. The simple reason is because of this pull, what happens? It becomes scaly like a fish. So if you are pushing your hand parallel to the way in which the scales are, then it's okay. But if you want to push your finger, press it and push it against the motion, then it bleeds. You get a cut, you get a deep cut if the rock is strong enough. That is how you know where was the movement of the fault plane? How did the fault plane move? So say for example, if the fault plane has moved like this, so if you place your fingers strong and move it along, nothing will happen. If you do the opposite, you're going to hurt yourself. So that's how you find out fault movements. So slick and slides, fault gouges, these are important evidences that tell you that there was faulting at that particular place. Now for irrotational fault, as I told you, the structures on the hanging and the footwall, they don't change. They don't change at all. The orientations are the same. Only thing here, the movement is, if you see the fault plane, and if you do the strut and you do the strike slip, so this is the direction of the dip, and this is the direction of the strike. So here you can see when the movement, this is the strike and dip of the fault plane. This is the strike and dip. Here I can't show you. Here there's a strike and dip of the fault plane. Here, why it is called a strike slip fault? Because the movement of the fault plane is parallel to the strike. That's why it's called a strike slip fault. That means the fault has moved parallel to the strike of the fault plane. Parallel to the strike of the fault plane. Similarly, you can get something like dip slip fault. Dip slip fault. Dip slip fault means the next slip of the fault plane, the next slip on the fault plane is parallel to the dip direction of the fault. So in strike slip fault, the movement along the fault plane is parallel to the strike of the fault plane, but dip slip fault is where the next slip is along the dip direction of the fault. And also, she will draw it after I finish. There is something called an oblique slip fault. Oblique slip fault, that means the movement is neither parallel to the strike nor parallel to the dip. It's oblique. So the next slip is oblique to the fault plane. So, say for example, in this, if this is the fault plane and this is the strike and this is the dip, so the movement, if it's like this, then obviously this is the strike slip, this is the direction of the strike slip, this is the direction of the dip. So you can draw a parallelogram of forces. So this will be the net slip component, this will be the dip slip component. So if you know the total amount of slip and you can resolve it parallel to the strike and perpendicular to the strike, so the amount of slip on the dip you can find out, and the amount of slip on the dip and the strike you can find out. You can do both. So this is what is a normal fault, this is what is a reverse fault, where the hanging wall moves up relative to the fault plane. There are two other things that is important. Within the reverse fault, there are two other types of fault. One is called a thrust. Now this is also important. It's of the type of reverse fault, you get something called thrust fault. Thrust fault is when the dip of the fault plane is less than 45 degrees. The dip of the fault plane is 45 degrees and less than 45 degrees. Then you call it a thrust. A thrust means this movement, this fault plane dip is less than 45 degrees. And there is something called an overthrust. Overthrust. Here, the dip is less than 15 degrees. So you can understand, for overthrust planes are very shallow degree. Have you understood? So there are reverse faults, when the dip is greater than 45 degrees. The same reverse fault, if the dip is less than 45 degrees, it's called a thrust fault. If the dip is less than 15 degrees, then it's called an overthrust fault. All of these are reverse faults. Right? And you know from my earlier lecture that thrust fault falls in the zone of shortening. So essentially, when you have a thrust fault, you have the zone, it is almost perpendicular to the zone of maximum compression. Whereas in a normal fault, the normal fault forms during extension. So on this direction, you have sigma 3 in this direction, which is the direction of extension. So normally thrust faults form in zones of crustal shortening. So in subduction zones, for example, where there is crustal shortening, you are expected to get thrust faults. Whereas if you go to the mid-oceanic ridges, where the major dominant force acting is extension, you are supposed to expect normal faulting. I don't want to go into this, but research have shown, mathematical modeling has shown, that normal faults are also characteristic in zones of shortening. But we don't go into that complexity. I think you will be taught, or whatever it is, in the senior class, at least the geology students. So you must remember this. You must remember this. Normal faults form due to extension. Due to extension. So sigma 3 is in this orientation, and this is, as I told you before, sigma 1. This is sigma 1 and this is sigma 3. So the thrust fault is in the normal faulting, the movement is the extension direction. Whereas here, this is sigma 1, this is sigma 1, and so this is the direction of, major direction of shortening. You get reverse fault, and thrust fault if the dip is less than 45 degree, over thrust if the dip is less than 15 degrees. So this is, and this is strike slip fault, as I told you, because the net movement is parallel to the strike. Net movement is parallel to the strike. Here you see it is counterclockwise, so if you are standing anywhere, you will see any marker to your left. For example, if you're standing here, your marker is to the left. If you're standing here, your marker is to the left. So that means this is a sinistral strike slip fault. Here, as shown, it's a sinistral strike slip fault. But you can also have a dextral strike slip fault. So in a dextral fault, what will happen? If you're standing in the fault plane on a marker, you will see the marker to your right. And in a sinistral fault, if you stand on the line, you will see your marker horizon in the other path standing to your left. So that is what is sinistral and dextral. But the common thing about it, regardless of the movement is parallel to the strike of the fault plane. Right? So these are the different types of faults. Now, I will ask you to make a reading for yourselves. There is something called Anderson's, you write down, Anderson's theory of faults. Anderson's theory of faults. So what it does is, it relates the strain field, sigma 1, sigma 2, sigma 3, and the type of faults. And this you have to read yourself. I have already told you a little bit, but you can read it for yourself. Anderson's theory of fault. This is the very backbone of faulting, to understanding faulting in rock zones, where it relates the strained soil, sigma 1, sigma 2, sigma 3. Remember, sigma 1 is the zone shortening, sigma 3 is the extension, and sigma 2 is the intermediate axis at 90 degree to the other two. So you must read up Anderson's theory of faults. It is not necessary for me to do it. You can read it up and you can find the answer. I have already told you a little bit. The background should be enough. So now we come to the rotational faults. Rotational faults are dominantly of two types. One is called a hinge fault, as she has written, hinge fault, where there is a fault and one block simply moves with respect, the hanging wall moves with respect to the footwall. So what happens? The orientations of the structure of the footwall becomes modified. The orientations modify, which is very different for irrotational faults. In irrotational faults, all structures and the hanging wall and in the footwall, they remain the same. Only there is translation, no rotation. No rotation is involved. But in rotational faults, this is what happens. So this, in hinge faults, this material is hinged at one corner, and then the hanging wall hangs down or rotates with respect to the footwall. And the other fault that is here, this is called a scissors or a wrench fault. Scissors or a wrench fault. It's more like a scissors. You know, you are pressing this, so you're pressing this. here the movement, as you can see, as she has drawn, the movement is like this, and here the movement is like this. So it's not hinged at a particular point, it's more or less in between, where the hanging wall moves, rotates around the foot wall. So this is the hinge area along which it rotates, right? So these are the different types of faults. Now you must understand one thing before we conclude this, that there are structures. Say for example here, there is a particular, say, dike that cuts this bedding plane, and this dike is displaced. So what happens here, you see, if I draw this line here, which is the strike, and this is the dip, and I draw this, the trace of this on the fault plane, this you see is the pitch. The angle between the line is what? A particular dike. The line and the angle with the horizontal, which is the strike, and this is called the pitch. So you remember this, that when you have a faulting, there might have been structures in the original unfaulted block. When you fault, the structures are displaced. They are not, orientations don't change, but they are displaced. And this displacement causes the fault plane to be exposed. Once the fault plane is exposed, then all the structures that they were, you can see it on the fault plane, right? And you can find the relationship of the fault plane. So you can find out the pitch of the fault, pitch of the marker horizon, say dike or a bedding plane on the fault plane. So remember this, the first thing is, how do you identify a fault plane? The fault plane is first identified in many ways. It's obviously identified by displacement of marker horizon, sudden displacement of marker horizon without folding. That's what is faulting. And the fault plane, if you happen to identify, very smooth, extremely well faceted, is extremely smoothly faceted. And you get, because of the intense crushing, you get fine powders, ultra fine powders that look like talcum powder. Ladies normally use that. These days I see men using more. But anyway, so you find those powders lying at the foot of the fault plane, and these are called fault gouge. And the other thing that you find is silica slides. I told you a little bit about this. These are striations in the fault plane made by very resistant minerals scratching on the fault plane. The silica slides are very important because they tell you what is the total amount of slip, which direction it slipped, which direction the movement was. So they are extremely, very, very important. These are some of the features of a fault plane. And irrotational faults, three types: normal fault, reverse fault, circuit fault. Rotational faults are two types, so thrust fault and overthrust faults. Now just before she will draw the diagram of an oblique slip fault and show you the different features of the fault plane. But before doing that, I just wanted to say this. I think before she draws the diagram, we will make that the final diagram. I want to tell you a term which she will, when she draws the diagram, you will find it a little handy. Say for example, you have a faulted block. And you can see it's a normal fault. Okay? So now, say there was a band here. Okay? And you see the band repeating itself. Or for example, this point is here. Now, you can project this point vertically so that it makes the horizontal this. Have you understood? Now, this has a term. This is called heave. Heave. And this is called the throw. So these two terms are very characteristic of faulting. Heave and throw. Heave is the displacement on a horizontal plane. Have you understood? Which is essentially formed, say this point and this point were the same before. So you know this point has moved here. So if you put a vertical line and let it meet the horizontal at this plane, so what happens? This vertical measurement, this is called the throw of the fault. Throw of the fault. And this horizontal displacement is called heave. So you have heave and throw of a fault line. Right? Other than net slip, strike slip, dip slip, net slip. So there is another two components, which is heave and throw. Heave, throw is this, the vertical separation between the point displaced on the hanging wall and a vertical point parallel to the one in the footwall. That is called a throw. And this horizontal displacement is called a heave. This is just to tell you before she does. Now before she does it, she will show you the diagrams. I will just try and conclude this with a problem. Since we have just talked about it. Say, it's like this. A dike is intersected by two faults. Dike is intersected by two faults. One fault dips 60 degree towards 120 degree north, and the other one dips say 60 degree towards 40 degree north. Right? These are the two fault planes where the pitch of the dike on the fault plane, the pitch of the dike on the fault plane A, is say 30 degree from northeast, right? And this one is say 45 degree from southeast. What is this values? The pitch of the dike on the two fault planes. Then the question is, find A, the attitude of the dike. The attitude of the dike. And B, what will be, find the pitch of the dike on a vertical dike trending east-west. These are the things that you have to find out. So, I have given you the data, this is the data that I have given you, and this is the question that I have raised. What is it? A dike is intersected by two faults. The one dike has this attitude, 60 degree towards 120 degree north. And the pitch of the dike is 30 degree from the northeast. Right? And then you have another fault plane which is 60 towards 40 degree north. And the pitch of the same dike is 45 degree from the southeast. Now what is asked is, find the attitude of the dike. That's the first thing. And second, the pitch of the vertical dike of the pitch of a vertical fault, trending east-west. So how do we go and solve this problem? Let's see. So since I have been drawing several of this problem, I will not go into the details of dip line and strike line and all that. That you should know that I am already doing it. So 120 degree is this direction. Say this is 90 degree, and this is 180 degree, and this is 270 degree. So 120 degree is roughly here. Roughly here. So if it is roughly here, then this is the dip line, and so the dip here is 60 degree towards 120 degree. So this is 1 point. This is 60 degree towards 120 degree. Maybe I will take it a little deeper. This is 60 degree towards 120 degree. And this is the strike line. And this is the strike line. And these are the 2 points of the fault plane as well. So the fault plane now looks like this. The fault plane looks like this. Have you understood? This is the fault plane A. This is the fault plane A. And what it says, the pitch of the dike is 30 degree from the northeast. 30 degree from the northeast. This is on the horizontal, 0 degree. This is 90 degree. So 30 degree will be somewhere here. So I will draw this point as the pitch of the dike on plane A. I will erase the rest because it creates confusion. So we will erase the rest. So, important, this point, what is this? This point is the point where the dike, I don't know what's the orientation of the dike, but the dike intersects A here. Right? Now let's look at the other possibility, other fault plane. It says dip is 40 degree, 60 degree towards 40 degree north. So this is 0 degree, this is 90 degree, 45 degrees here. So 40 degrees should be somewhere here. So 40 degrees should be somewhere here. If I do that, and again, I draw the dip line, and I draw the strike line, which is perpendicular to it. So, now, 60 towards 40 degree north. So if it is 60, then maybe this is 1 point, this is the other point, and this is the other point. So the fault plane essentially is this. This is B. I will just, for you, I will give you the data here. This is 40 degree, but I think you can understand. This is, all these lines you can understand. So I will erase it again, the dip lines and the strike line, so that it's less confusion. You don't have so much confusion. Now, So now what we have? We have now this point where the fault plane intersects fault A, and this is the plane where no, I didn't do it. Sorry. Now, on this plane, 60 towards 40 degree north, the pitch of the fault plane is 45 degrees from the southeast end. So this is southeast, this is east, this is south, this is southeast end. So here it is 90 degree. So what we do is 45 degree should be here. So this is 45 degrees. So this is another point of the fault plane, because this is the point where the fault plane, where the dike intersects fault plane B, and this is the point where the dike intersects fault plane A. So if I have to take that, then the fault plane has to pass through this point, and then the fault plane becomes very unique. The fault plane becomes very unique. So what I do is so this is the fault plane. This is the fault plane. This is the fault plane, FF. Have you understood? This is the fault plane because it passes through these 2 points, which are basically the pitch of the fault planes, or pitch of the dike on the 2 fault planes. So this is the fault plane. How is its attitude? We can see this. How its attitude? We can draw. If I draw this, then this is the strike. This is the strike line of the fault plane, and 90 degrees to it. And 90 degrees to it, this is the dip line, this is the dip line, and this is the strike line. So now, if this is the dip, then this is the plunge. So this is the dip of the fault plane, and this is the direction. So what is the direction? For answer A, for example, this would be about 40 degrees, the dip 40 degrees towards, say, 115 degree north, rough. That is the attitude of the dike. That is the attitude of the dike. Now what happens next? We have to answer question B. What is this? What is the pitch of the vertical fault trending east-west? Now this is interesting. How do you draw it? It's a vertical fault and is trending east-west. So now, that line is this line, because this is east-west, and this will appear to be a straight line because it's a vertical line, and this fault, which is this one, the pitch of the vertical fault trending east-west, this is the intersection of the dike, which is the dike, intersection of the dike with the east-west trending fault plane. So this angle would be roughly around 35 degree and from east. 35 degree from the east. But this is a vertical plane. So the pitch is equal to the plunge because the plane is vertical. So if you have a vertical plane, the pitch is equal to the plunge. So that means this dike in black should appear at 30 degree on a plane that is trending east-west. So again, what did I do? First I found out the attitude of plane A, fault A. And I drew this point, which is the pitch of the dike on the fault plane. And then this point therefore lies on the fault plane. Then I drew the second fault plane and found out the pitch of the fault plane of the dike on that fault line. So now what you have, 2 points that both lie on the dike. And therefore, I draw a great circle which fits it. Right? And these 2 points give me the strike line, and therefore perpendicular to it is the dip line. So when I do this, I find out that it is relatively 40 degree towards 115 degree north. I may be a little wrong, but that does not matter. The idea is important. 40 degree towards 150 degree north. What did I do next? I've been asked to find out the pitch of the dike on a vertical fault. This is the third fault. Pitch of the dike on a vertical fault trending east-west. So I draw this line. What is this? This line is the fault plane. Why is it straight like this? Because it's vertical and it trends east-west. So this is the only line that can happen, and this line intersects the black dike line at this point. So this angle from the horizontal to this should be the pitch from the eastern end, which is say 35 degree from the east. It is pitch, but the plane is vertical, so it's a plunge. So pitch is equal to plunge if the fault plane is vertical. Remember, I told you that there is a geometric relation between pitch, plunge and dip, and you have to find that out by reading it or deriving it. But if you're deriving it, you better check it out against the internet to find out what is the actual value, because then that is what pitch on a check it out. The pitch on a vertical plane should be equal to the plunge. That's a check whether your derivation is right or wrong. So this is how I solve the problem. Okay, so now I hand it over to my student. She will draw you a oblique fault with all the features of a fault plane. And it's a little complex, and you know my level of sketching is just not there. It's horrible. So, no. So it takes a little while. Please wait. Yeah.
would have required another color to highlight this part.
There's no more.
Yes.
ঠিক আছে তুমি ওইরকম করে
I'm using a broken
এটাই করে
line.
দাও না
I'm using a broken line.
হ্যাঁ ডি হবে ওখানটা সেকেন্ড স্লাইডে একই ওরিয়েন্টেশনে হবে না নেক্সট লিখে
So,
AD parallel second slide. Eight. Google Pay. What's that? Okay. Back to 88. I'll call it. Okay, so thank you, Odisha, very much. Thank you. So now we have the complete diagram with the different things, and it's well done actually. The only thing, this is the foot wall. and this is the hanging wall. This point D was initially A. So the movement of this is from A to B. So this is what is called neck slip. And this is what the secant slides trace. So once you have the neck slip, it can be split into strike slip here. This is the strike slip, AB, and BD, or you can also draw this dip here itself. So it is like a parallelogram of forces. So A, B, and D, these are points on the fault plane. A, B, D are points on the fault plane, where this angle here on the fault plane is called the rec. Remember, it is measured from the dip direction. Have you understood? And this is called the pitch. As always, the neck slip has this pitch on the fault plane from the horizontal. And rake, remember, is the angle from the dip direction. Have you understood? So, from the 90 degree inwards. So, rake plus pitch is equal to 90 degree. So, it doesn't matter whether you match the pitch, then you know the rake. If you know the rake, you know the pitch. So, this is one triangle. Triangle ABD. And this is what he has shown. He has shown, remember, this triangle is in the fault plane. So, you have strike slip, you have neck slip, and you have dip slip. You could have also done a dip slip like this, like the parallelogram of forces. Would have been same. This and this would have been the same. So what happens? Dip slip is the slip along the dip direction of the fault plane, and AB is the strike slip. Basically, there should be an arrow here. There should be an arrow here because that is the slip directions. So essentially, this is on the fault plane, and this is what the first triangle ABD is. The second triangle here, you can see is written ABC. Now this is A, B, and C. This is on the horizontal plane. Remember, this is on the horizontal plane. Right? And here you have the strike slip AB, correct? The heave BC. That, remember, I drew the diagram where you draw this point vertically up so that it pierces the horizontal. So this is BC, is the heave. And this is the horizontal throw. Last time I wrote only heave and throw. But this is the horizontal component of the throw. This line AC. Remember, the triangle AC is on the horizontal. The triangle ABD is on the fault plane. And this triangle ACB is on the vertical plane. So on the vertical plane, you have AC. No, I think you have missed it. ACD, right? ACD. So this is ACD, right?
So BCD, the dip.
Oh, BCD. No? Yes, sir. BCD, yes. So BCD, BC is the heave, CD is the vertical throw, and BD, this is the dip slip. So this is a vertical plane. Remember, ABC is a horizontal plane, and ABD is a plane on the fault plane. Be very careful. This is how measurements that you make on a fault plane. Your first, essentially what your first thing is, you have to find out the neck slip. And this is not very easy unless exposures are very, very good. That this point has moved. The secant slides will say in which direction the movement is. But which point to which point, that would require two marker horizons. Have you understood? So here, it's very easy to draw things on the board. When you go to the field, it's not so easy. So this is A moves to this neck slip. On the fault plane, ABD, AB is the strike slip, BD is the dip slip. You could have also drawn BD this way. It doesn't matter. The angle between the strike and the neck slip is the pitch. From the dip towards the dip slip is the rake. Then you have the plane ABC, This is a horizontal plane. How was C done? You take this point and raise it vertically above till you reach the horizontal. And then you have ACB. AB, as you see, is tricep. BC is heave. And horizontal throw is this. And then you have BCD. What is BCD? BCD is a vertical plane that contains AC, CD and AD. What is CD? CD is the vertical throw. This one, BD is the dip slip and B is the heave. So, I come to the end of this set of lectures, Introduction to Earth Science. It was quite an experience for me because when I started, I didn't know what I was doing. So one of my former students, now she is an assistant professor somewhere, she showed me how to do it, and now my present student on Nesha, he has helped me tremendously. So I thank her very much for helping me out, and I could do it faster because of her only. And I thank her very much. There will be an exam. 17th I'm completely booked. 19th the semester ends. So either on 16th or 18th you have to take an examination. I will write it on the Google Classroom whenever I am ready. And this will be an examination of 50 marks. So I have still not arranged the questions, etc. So I don't know. But I know one thing, as agreed upon, I will give you 3 minutes between the end of one question and submission of the second question. If there is any more delay, I will not be able to do anything. And again, as a word of caution, if I see that there are 2 scripts which are same, I will cancel both and give 0 to both. So please don't copy things. Don't send anybody, and you please don't copy anybody. Nobody says give something unless it's asked for. That condition does not exist. But I will scratch both if I find the answer script same. Because under no circumstances 2 questions can be same. It is impossible. Right? So we need to find out a date, either on the 16th or 18th. Forenoon is better because it will take some time. So what I will say, and the whole visual, all the video lectures is the course content. So there is nothing about it. So I think it will be 1.5 to 2 hour question set. And in between I have to give gaps, so I don't know. You better keep 3 hours free for yourself. Right? Thank you very much. I hope you learned a little bit about the earth, how the earth works. It would have been better if I could have taught you in the class. But given the circumstances, I hope that you have learned a little bit at least. Thank you. Once more, if you have any questions to be out, then you can invite me on a Google Classroom at an appointed time, and I can try and answer some of your questions. But there is a lot to read. Most of you have not done well in your first 2 tests. So this is your last chance. Otherwise, several of you will fail. Right. Thank you.